Hey guys, in this video we're going to be talking about what is a derivative and who created it or discovered it, and more or less how he created slash discovered this concept. So the first thing that we're going to talk about is serial killers. Nah, I'm kidding. Let's talk about Isaac Newton. Isaac Newton is a famous English mathematician and scientist who studied physics, and in his study of physics he was trying to figure out the how to calculate the instantaneous rate of change of different functions. Particularly, one of the functions he was looking at was position, and the instantaneous rate of change of position is velocity. And he was also looking at the instantaneous rate of change of velocity, which is going to be acceleration. We're going to see in this video that the instantaneous rate of change, which is the derivative, is going to be finding the slope of the tangent line to a curve. Okay, before we get started, let's look at a few concepts that you might not be familiar with. First, let's talk about a secant line. All right, so a secant line intersects, in this case, a circle in 2 points. But we can think of a concept similar to this for any graph of any function, where a secant line is basically going to intersect the graph of a function at 2 points. A tangent line is a line that intersects the circle only once. And take this concept and apply it also to any function. So here we have the tangent line to a curve. It approximates the graph of the function and touches exactly at one point and then continues on. Okay, it can intersect at other points, but what we're looking at is a line that is tangent at this point here, that is green. Okay. Alright, so let's look at what is a derivative. So we're going to analyze a function that you're all familiar with, y equals x squared. So this is the graph for y equals x squared. It's the parabola, which you are all familiar with. Suppose that we're trying to find the instantaneous rate of change at the point where x is 0.5. Okay, and f of x in this case is going to be 0.25. So that is this point A. Let's zoom in a little bit so we can have a closer look. Well, we don't really know how to do that, but one way to approximate instantaneous rate of change is to find the average rate of change between 2 points on the graph. So let's pick another point on the graph. Okay, so we have point B with coordinates 1.5, comma 2.25. If I was trying to find the average rate of change for this function between these 2 points, then that's a very simple thing to calculate. All we have to do is look at the difference in the value of the function, the difference in the y's, and divide by the difference in the x's. Okay, so for this particular set of points, we would have 2.25 minus 0.25, and we're going to divide by 1.5 minus 0.5. Okay, and we have an answer of 2. The average rate of change for this function between these 2 points, A and B, is 2. Now this formula might look familiar for you because all we did was subtract the y's. So suppose that B is 0.2, so we have y2 minus y1, and we divided by x2 minus x1. And this should look super familiar because this is the formula for finding slope. Okay, so what slope exactly are we finding here? Well, let's have a look. Since we are using point A and point B, we can always draw a line between A and B. So the slope that we're finding is for the line that connects points A and B, and we can see that this is a secant line to the curve of y equals x squared. Okay, now let's remember that what we're trying to do is to find the instantaneous rate of change at point A, not the average rate of change between 2 points, the instantaneous rate of change. Well, if we use the secant line, if we use the slope of the secant line, we know that we have the average rate of change between 2 points, and that's going to be an approximation for the instantaneous rate of change at point A. But how could we make it better? Well, one idea, Isaac Newton's idea, is to take this point B and bring it closer to point A. Okay? So we're going to bring it closer. And we're going to bring it closer and closer. Closer and closer. Okay? We can bring it so close that when A and B are so close that you can barely tell the difference, then that is going to be an excellent approximation for the slope of the tangent line. Okay? And the slope of the tangent line is going to be our instantaneous rate of change. But now, this process of taking a number and looking at where it is approximating when we're moving x, if you remember from our limits video, when we do that, what we're actually doing is finding a limit. What limit exactly are we finding? Okay, so how can we calculate in a more general way the slope of a secant line? Well, we're going to use point B and point A. Notice that what I have is that point A is 0.5 comma 0.25, and all I'm going to do is take x values that are very close to 0.5, and the way I'm going to do that is by defining B as 0.5 plus h, and h is going to be the difference in the x values between A and B. And our idea is to make h very, very small. Okay, we have a slider here so that we can move it the way I've been showing you, and we're going to make it as close to 0 as possible so that A and B are basically the same point, and so that we have a tangent line. To calculate the slope, again, we have to do the difference in the y values. So for example, we have y2 is f of 0.5 plus h, 2 is f of 0.5 plus h, minus y1, which is going to be f of 0.5, and we're going to divide by the difference in the x values. So we have x2 is 0.5 plus h, and we're going to subtract x1, which is 0.5. Okay, so this gives us this general formula is going to give us the slope for any point that is coming close to point A. Okay, so we can move this h, and if you look at the calculation for slope, is going to calculate, and we're going to try to find the limit when the h is very, very close to 0, which is going to make point B and point A very, very close together, almost the same point. Okay. Now, one thing that we can do here to simplify the calculation a little bit is to simplify the denominator. Here we have 0.5 plus h minus 0.5. So we know that the 0.5s can cancel out, so we can leave h. Okay, and this is going to be the general formula for the slope of a secant. Now here's the trick. How can we find the slope of the tangent line, which is going to be our instantaneous rate of change. Well, what we're going to do is take the limit as h is approaching 0, okay? And notice that when h is approaching 0, then x is approaching 0.5 for point B, okay? Because I'm adding something that is very, very close to 0, so it's almost 0.5. That means that point B is going to be very close to point A, okay? We're going to take this limit of the calculation for this slope, 0.5 plus h minus f of 0.5. So remember, this is the difference in the y's, and we're going to divide by the difference in the x's, which we already know is, when we simplify, is going to be h. So this limit is going to give me the slope for the tangent line to the curve y equals x squared at 0.5. And this, my friends, is what is known as a derivative. In particular, this is a derivative of the function f when x is 0.5. Okay? Now, here's the thing. This is only the special case of x equals 0.5. So what I'm going to do is change up this formula to make it general. So how would the derivative of x look? Well, super simple. All we're going to do is take the limit as h is 0, as h is approaching 0, and we're going to change our formula to f of x plus h minus f of x over h. So the top is going to be the difference in the y's, and the bottom is the difference in the x's. Notice that when h is approaching 0, then f of x plus h and f of x are almost equal, because h is very, very close to 0. So I'm almost not really adding anything. Okay? And when h is approaching 0, the x values are almost the same. That's why the bottom is approaching 0. Now, something to keep in mind is that h can never really be 0. Because when h is 0, then what we're going to have when we do the calculation for the slope is an error. Okay, you saw it there for just a second, an error. It's undefined because you cannot divide by 0, and that's why we need to take the limit. Okay, well, that's it for this video. This is the definition of a limit. We're going to have an activity whenever we can be back in the classroom to show you how to calculate the limits using the definition, and something fun for you guys when we come back. Thank you for watching. It's been a pleasure to be with you guys again. That's it for now. Until next time.